Hello, and thank you for joining us today for today's webinar on how PEER and HOMER can help you determine the resilience of your hybrid system. My name is Tricia Fitzpatrick, and I'm the Marketing Manager at HOMER Energy by UL. We have a full agenda for you today as we explore two solutions that help you demonstrate project value, reliability, and resilience from feasibility through completion. The Honorable Katherine Hammack is the Director of Special Project at Green Business Certification. GBCI drives implementation of the LEED Green Building Program. And today she will present the PEER program, which aims to transform the power sector just as LEED transformed the building sector. PEER, or Performance Excellence in Electricity Renewal, is a rating system that evaluates a power system's reliability and resilience performance after construction is completed. Honorable Hammack was a founding member of US GBCI over 30 years ago and is the former Assistant Secretary of the Army. Her focus today is on increasing resilience and reliability in power grids and advancing tools to improve the built environment. She is a graduate from Oregon State University with a degree in mechanical engineering, as well as a master's in business from University of Hartford. Dr. Peter Lillianval is the global microgrid lead for UL and founder of HOMER Energy, which is now a UL company. He has been at the forefront of the microgrid industry for nearly 30 years and has experienced and driven the adoption of microgrids and distributed energy. He received a Ph.D. in management science and engineering from Stanford University and joined the Solar Energy Research Institute in 1990, which became the U.S. Department of Energy's National Renewable Energy Laboratory, or NREL. He went on to become a senior economist at NREL and created HOMER there. Today, he will show you how HOMER modeling software helps you optimize your hybrid power system for resilience during 3 types of power outages. And so now I will turn the presentation over to the Honorable Katherine Hammack.
Thank you very much. I'm delighted to join you today. And we will be talking about measuring reliability and resilience. Let's take a snapshot of the world's worst global blackouts for the last 20 years. This outage chart presents the reason and impact of the outages. Major blackouts occurred due to technical faults and human errors, but natural calamities like hurricanes, rainstorms, snowfall, as seen here, have also taken their toll. And of course, the COVID-19 pandemic has significantly affected the energy and industrial sector. Another surprise just this last year was the winter storm in Texas in February, which led to the power grid putting at least 4.5 million Texans in the dark. As climate change continues to result in more severe weather episodes, the economic and environmental damages it creates is much higher. Losses totaled almost $3 trillion from recorded disasters between 2000 and 2019. Storms cost more than any other disaster type in terms of recorded economic damage, 1.39 trillion, followed by floods and earthquakes. The U.S. Department of Energy estimates that power outages alone are costing American businesses around $150 billion per year. Now, that's a lot of money that could be reinvested back into the economy. The truth is, having a resilient power source not only saves money, but also maintains the critical resources everyone needs to be safe and secure. The need for power grids or microgrids that should be reliable, resilient, safe, efficient, renewable, and smart has never been greater. PEER is the first comprehensive outcome-driven system for evaluating power system performance. It is designed to help industry stakeholders dramatically improve system performance by providing a framework for continuous improvement and performance assessment. Now, US GBC or GBCI is more often known for the LEAD program, which has a focus on sustainability in facility design, tenant behaviors, and site location. But it does not address the details of power received, whether it's reliable and of good quality, any other options to receive power, technologies to improve the quality of power, technologies to reduce power consumption. That is where the peer system rating system steps in. Peer looks at project performance from the power generation or transformer to the customer meter. Of course, distributed generation and microgrids can bypass or reduce transmission and distribution complexities. Peer sustainable power distribution has 6 guiding principles, which include a customer focus, applicability and flexibility, measurable performance, market transformation, transparency, and benefits for all. Peer sustainable power peer project, every peer project is a mark of leadership and an investment in the future. It is a commitment to continuously improving and doing good from human, environmental, and economic perspectives. Through certification with peer, we are encouraging quality and reliable power. That's what peer's mission is. Now, peer can be used for power system of all sizes, whether it's a building, a campus, a city's grid or a utilities territory, or even a transit system. Peer is a metrics-based certification program that measures power system performance across 6 categories. The first is reliability and resiliency. This category identifies strategies for the reliable delivery of electricity, preventing damage and reducing interruptions or power quality issues. The energy efficiency and environment category assesses the environmental impact of electricity generation and transmission, encouraging the adoption of clean, efficient energy. Operations, management, and safety addresses the safety of personnel during system operation, risk mitigation, maintenance of systems, asset utilization, and technology investments. While grid services looks at the customer contribution to grid services, investment, and innovation. The last 2 categories are regional priority and innovation and exemplary performance, to encourage projects to achieve exceptional or innovative performance. Sustainable system design comes from innovative strategies and thinking. Now, there are requirements or prerequisites for every project. The first is reliability performance monitoring, which assesses the average duration of power interruption and the average frequency of interruptions. Environmental performance disclosure and system energy efficient coefficiency disclosure measure and make public the environmental consequences of power generation, transmission and distribution, and the energy system's conversion efficiency. The triple bottom line analysis is to qualify the benefits associated with high performance, and then customer and load survey supports decision-making and planning on power quality, demand-side management programs, and other customer contributions. These are foundational requirements for establishing a reliable electric grid. The main goal of a power system is the reliable delivery of electricity through reducing power interruptions and minimizing power quality issues. Some of the peer credits that address reliability and power quality are the prerequisite that I just talked about, which discusses your average duration of power interruption, your SAIDI, and the average frequency of interruptions, which is your SAIFI. There is a reliability performance assessment credit to benchmark reliability to other projects. And then a distribution redundancy and auto restoration credit to improve reliability and resilience by ensuring that grid power can be supplied via multiple distribution pathways. The power quality capabilities credit assesses and mitigates poor power quality events through detection, prevention, and corrective actions. Now, strategies which can be implemented by the project for better power system reliability include infrastructure that supports continuous monitoring and recording of power interruptions in real time, a self-healing redundant distribution network with auto reclosers and smart switches that can always ensure power is provided reliably, and alternative sources of supply which can seamlessly provide power to the project in case of primary power supply failure, can also support the islanding capability of a project. Peers certified a municipal utility system, Chattanooga EPB, which has a redundant distribution network. They increase the number of smart switches and auto reclosers, which automatically test and re-energize a circuit and can isolate the fault, providing power to other areas. And their system in Tennessee is twice as efficient as that of the primary power grid or other than municipal utilities. Power quality is important as variations in power quality can damage electronic equipment and cause inconvenience to customers. Poor power quality can also increase customers' electricity costs because of efficiency losses. Thus, a project needs to monitor power quality by having in place permanent integrated infrastructure to monitor the power quality in real time across the distribution network. And you can maintain the voltage profile and improve reactive power support at the substation or feeder level by implementing an energy storage system. Next to reliable power systems, building a resilient power infrastructure, which has the ability to resist, absorb, accommodate, and recover from the effect of hazards in a timely and efficient manner, is a need for all buildings. PEER recommends projects ensure power for critical loads and essential services is available during emergencies and to support community recovery after catastrophic events and grid failures. To provide power surety, critical loads such as elevators, some lighting systems, data centers, telecom, etc., should be supplied with redundant sources of supply or uninterruptible backup power at or near the load for enough time to stabilize the load and discontinue service safely. Essential services like community shelter, healthcare, fire services, etc., should be supplied with highly reliable power for at least 1 week, although power does not need to be continuous or offer full functionality. Projects need to be prepared to face any kind of threats to the power system, and identifying critical loads and determining their minimum daily runtime is certainly one of those priorities. Providing backup power and priority restoration for identified critical loads and blackouts or brownouts. Maintaining the required amount of fuel for the backup power system to support those minimum runtimes, or providing power supply through a renewable energy system, solar or wind, that does not depend upon external fuel like gas or diesel to meet essential services, and then having in place power independent communication systems, which may be wireless or fiber. The external threats that we discussed can be reduced by implementing strategic design for the backup power system with seamless transfer, so the project can transfer from being grid connected to islanding mode without a power interruption. Ride-through is a capability that allows a project's grid to continue to operate while it transitions from grid connect to island operation. A comprehensive risk analysis and failure mode identification evaluates the likelihood and consequence of an incident, deciding how likely it is that injury, damage, or loss will happen, and what the effects will be if it does happen, identifying all possible failures in a design. And of course, you can harden the mission critical infrastructure by burying electric cables underground or protect them in conduits or underground tunnels. The electricity system has long existed as a black box for many customers. They receive a bill at the end of the month, make a payment, and trust that their electricity will stay on. But that's changing as automation, intelligent control, and distributed resources are more readily available. Customers become an increasingly valuable resource to grid operators. This brings up the need to assess customer contribution to grid services and think about investment and innovation. Peer credits that offer strategies to address customer contribution to grid services include a load duration curve optimization credit to bring a peak load closer to the base load, demand side management credits, which encourage achievement of permanent reductions in energy demand and consumption through conservation, or an aggregation credit, which is the pooling of customers and loads to balance demand and supply. Projects can work to improve their customer engagement and to provide better customer satisfaction through smart technologies like automated metering infrastructure, or AMI, to enable customer participation in grid services. And smart meters enable bi-directional communication between the customer and utility that can encourage load reduction in response to demand signals. Also, AMI provides net metering capability, which supports local, renewable, and clean electricity generation. The signals can be sent to customers then to reduce load during peak periods when you have that two-way communication. Customer engagement through grid services can be improved by having a master controller system connected to all the major assets of a project or system, thus promoting distribution automation. And you can support higher level applications of load management, monitor power system operation in real time, optimize loads to meet the requirements of the main grid, and perform remote control of loads and analysis of system operation through a dedicated communication infrastructure. The environmental impacts of energy generation, transmission, and consumption are of increasing importance around the world. Now, it's been reported that coal is the most water-intensive method of generating electricity. Every 3.5 minutes, a typical coal-fired power plant withdraws enough water to fill an Olympic-sized swimming pool. And I'm not even going to talk about the emissions characteristics of coal. But by substituting renewable energy, your greenhouse gas emissions and water consumption are reduced, while the environment and human health are improved. So assessing the environmental impact of electricity generation, transmission, and distribution, and increasing the adoption of clean and efficient distributed energy technologies is paramount. The peer program addresses environmental impact reduction through the environmental performance disclosure prerequisite, which evaluates the CO2, SO2, NOx, water, and waste impact of your power system. The renewable energy and carbon offsets credit recognizes renewable energy in the system or carbon offsets that might be purchased. And the environmental impact disclosure and management credit looks at how you're handling the environment in and around elements of your project. Environmental impact can be reduced by renewable energy generation or installing an energy storage system like batteries, which store the power from local generation sources and then can be utilized during power outages. Encouraging customers to be prosumers, both producers and consumers of energy, and then district energy systems with perhaps thermal storage support the heating and cooling and electricity needs of a project. The peer certified Ameren microgrid is one of the few microgrids that operates at utility scale voltages between 4 kV and 34.5 kV and has multiple levels of control. During normal operations, the microgrid uses the on-site generation resources to optimize the efficiency of the power system, and it powers just under 200 residential and commercial customers with a combination of natural gas generators, battery energy storage, solar, and wind generation technologies. Now, peer is designed to help dramatically improve system performance by providing a framework for continuous improvement and performance assessment. It helps project teams benchmark reliability and environmental performance and plan to improve power availability and mitigate emissions, to improve building resilience through power system hardening techniques such as undergrounding and critical design of infrastructure, delivering values by ensuring power for life-saving systems, reducing operational failures through failure mode and effect analysis, through interruption monitoring and comprehensive risk assessment, reducing environmental impact through efficient and renewable energy systems that have lower impacts on nature, and cost savings with preventative maintenance programs that reduce damage and loss of equipment and associated infrastructure, and then overall demonstrate leadership at a global scale by receiving an independent third-party certification. When peer certified University of Texas, Austin, their microgrid, they stated that the peer program made us think. It asked us questions we hadn't thought of before. So when we went in for our first certification, we didn't achieve the score that we thought we could. So when they recertified 3 years later, they had used the peer program to identify areas for improvement and a roadmap for improvement. They certified at a peer platinum level only 3 months prior to the storm in Texas. And they were able to ride through that storm, providing University of Texas, Austin with power. They had no downtime, and so they were able to man warming centers and provide food services for students and faculty. Peer is already impacting electricity delivery across cities, campuses, municipal utilities, and transit systems with certified projects that are providing reliable and quality power to almost 8 million people globally, saving 510 million kilowatt hours of energy a year and realizing over 54 million in annual cost savings. And in addition, renewable energy technologies and peer projects mitigate 21 million metric tons of CO2 emissions a year and create over 4,700 jobs per year in installation and maintenance of renewable energy systems. Here are a few of the global peer leaders who have contributed to sustainable electricity transformation, clean energy adoption, and green jobs around the world. We add more projects every week. Now you can learn more about peer at peer.gbci.org with access to resources, guides to certification, technical reports of certified projects, case studies, and peer articles. And the complete peer reference guide is also available online. And now, Peter, why don't you explain a little bit about HOMER Energy?
Thank you, Katherine. Yeah, and thank you all for being here, and thank you, Katherine, for that description of your program. And now I'm going to talk a little bit about HOMER and how we model reliability. And I apologize if people have been to our webinars before. The first part is sort of an introduction to HOMER for those people who aren't as familiar with it. It stands for the hybrid optimization of multiple energy resources. We're all about hybrids, and we're all about being as technology and vendor agnostic as possible. I'll go into more detail in a minute, but it's both a simulation engine of how systems perform, an optimization software for coming up with the best design for a microgrid, and it has its own built-in sensitivity and risk analysis because there's always a lot of uncertainty about your inputs and et cetera. So the goal is to find the most attractive hybrid system. A little history, you know, I've been working with HOMER and hybrid systems since the early 90s. It was developed originally at the National Renewable Energy Lab as a response to the Earth Summit in Rio in 1992. It was a research project back then. It's gone through lots of iterations since then, which I won't go into all the details of. But by 2009, it was clear that there was a distributed power industry starting to happen, and it was time to commercialize the software. So we created HOMER Energy as a private company, spun up out of NREL with the exclusive license, grew it for 10 years to be acquired by UL 2 Decembers ago, like 15 months ago or so. In that time, over 250,000 people have used HOMER. And you can see over on the right sort of a map. It is a map showing where projects have been modeled with HOMER. Some places like the Philippines are completely covered. You can see Kenya and Nigeria and other parts of West Africa are sort of hotbeds, as is India and Australia. So there's a huge amount of data behind all of this. We have 4 million HOMER files describing over 90,000 projects that have been modeled with HOMER. And over something like 120,000 people have opted into our network and get our monthly newsletters and other outreach efforts on our part. So we really are a de facto global standard. Let me talk a little bit about UL. That's kind of the new piece to us, although now that it's almost a year and a half, maybe it's not quite that new. But UL's been doing renewables now for over 10 years. UL as a company has been around since 1894, and they're the preeminent safety experts starting in the US, but now they've gone really global with offices in 100 countries and projects in over 140 countries. This map just shows the biggest offices. We've been involved with over 100,000 hybrid projects since 2014. We're the forecast providers for over 100 gigawatts and the main point is we have over 500 renewable energy experts. And so being part of UL has now allowed us to really expand rather the scope of our work and to include a lot of advisory work. Instead of just selling the software, now we can really help people with the software. So here's just an overview of some of our users, and the point of this slide is just to show the vast diversity of users. across the entire ecosystem of hybrid power design, distributed power. We're getting a little more into front of the meter utility scale projects as well. So what is HOMER? It's a piece of software, and it's for optimizing the design of hybrid projects. We started in the microgrid world, we expanded into more general distributed generation, and now we're doing more with front of the meter utility scale stuff. So you obviously need to know the economics. So, what do different components cost? What are your interest rates and discount rate, et cetera? For distributed projects, the load profile is incredibly important. You need to know your renewable resources, and we not only have a library of system components, but we also have databases for the renewable resources around the world and for typical load profiles for different building types in different locations. So those are the inputs. It goes into the software to do the analysis. In the innermost core is a simulation engine that says how would a system actually operate, hour by hour or minute by minute if you have the data at that level, or 15-minute, whatever intervals you have. And so when does the battery get charged? When does it get discharged? Are you importing or exporting power? Do you need a backup generator? If so, when does it run and how much fuel does it use, et cetera? So that tells you how one system operates. And it can be for 1 year, or you can do it for 30 years or whatever your project life is. So that's one system. So the optimization algorithm that's built around that will simulate hundreds of different systems and find the least cost system for distributed projects or the most profitable project for front of the meter projects. That's the optimization loop. Tells you what's best. But again, it's only telling you what's best for one scenario. What if prices change? What if utility tariffs change? What if you really didn't have that good an estimate on the cost of certain things? You want to do sensitivity analysis on that, or load profile, et cetera. We believe sensitivity analysis is incredibly important for understanding the risks associated with a project and making good decisions. So we built that in sort of an automated feature within HOMER. And of course, you get results, and they include how would the system perform, high-level results like your return on investment and your internal rate of return, more detailed results like how does each component operate, what's the life of the battery going to be depending on how it's being used. And then you can drill down and look hour by hour, or again, minute by minute if you did it that way, and look at actually how the HOMER modeled its operation over time and different seasons, et cetera. And we have a report writer that creates a report that's suitable as a proposal to a client. So that's an overview of HOMER. Now, let me talk about resilience now. And I'm going to start by describing the role of backup generators, because until recently, if you were worried about reliability and grid outages, et cetera, or if you lived in a remote area, whatever, you relied on a backup generator, a reciprocating engine, typically diesel, but actually propane is actually cheap, or LPG is actually cheaper and cleaner. And that was your only option. But that's all changed now. But there's an enormous number of these backup generators out there, and they do have some real advantages. They're very low capital cost, but they have high operating costs, and that means they're good for occasional use. And that's so if your outages are, you have a 2-hour outage once a year, that's probably all you need, frankly, unless you're really concerned about emissions and noise, et cetera. They do have those challenges. They're very noisy. They're polluting. They need constant maintenance, and if you use them very much, the fuel cost and the maintenance cost, it becomes a real problem. And that's what a hybrid system, or one of the things a hybrid system can really solve. So at HOMER, we distinguish between 3 really different kinds of reliability and resilience issues, 3 different kinds of outages. So in some parts of the world, there's regularly scheduled outages, especially some of the remote diesels will only run for a few hours in the evening, or maybe 12 hours a day, but they don't run all the time. And some places have rolling blackouts that are actually on a schedule. That's not that common, but I've seen it for sure. So that's one type of outage. Another type of outage is what's really common in utility systems around the world, in developing countries primarily, where the utility is just not that reliable. There's outages all the time. They're not very long. They might only be a couple hours or so, but they're just really frequent. So frequent short outages, that's a different kind of problem with a different kind of solution. And then in the US, we've gotten really concerned about these infrequent but extended outages. You know, Catherine's presentation had this, one of the early slides had this great bubble chart showing how big some of these outages have been, from Superstorm Sandy to the Texas situation most recently. The wildfires in California are probably the most significant one because they're going to keep happening. And the utility is cutting off power to prevent wildfires. So they're turning off power to whole communities, whole regions preemptively for days at a time when in a high wind, dry, high fire risk time. So those places all need some kind of power during those multi-day outages. So we call that resilience. We call the second one reliability, and the first one is a part-time issue. So they all are handled in a different way. Part-time diesel is very easy. We have a little control that lets you schedule when the utility service exists and when it doesn't exist. And like in this little picture here, the service is on from 8 in the morning to 11 in the evening every weekday, but on weekends it's just from 7 in the evening to 11 in the evening. And that's completely controllable, very simple, probably not the most important piece. This one is very important because most of the world has unreliable electric utility service. And so you just say, how frequent are they? In this example, I'm saying 100 outages a year, so like 2 a week. The average time is about 3 hours, but it varies quite a bit. And you can see these black bars, some of them are short and some of them are long, and it's kind of random. You can change, if you don't like that pattern, you can recalculate and create a new pattern. Another important feature is a lot of systems are you can save a lot of money in designing a system if you're only concerned with critical loads. You want to make a distinction between critical loads that you really need to power and non-critical loads that in an emergency don't need to be powered. And we have that capability here. It's not turned on for this picture, but that's actually can be very useful in the design of a resilient or reliable system. And then for resilience, which, for example, these extreme weather events, but now we're even worried about a variety of terrorist or cyber attacks, et cetera. There we're talking about outage in days, not hours. You can pick a specific date, or you can let HOMER randomize it. We think in most cases this won't happen every year, so you can say how the frequency issue is a little different. And what is the algorithm needs to think about this is, does it have advanced knowledge? Like with a hurricane, you've got advanced knowledge that it's coming, so you can make sure your batteries are full. But with an earthquake or an attack, or you don't have that kind of advanced knowledge, and that makes a difference to the algorithm. So so that's, we make a distinction there. So in conclusion, it's really important to understand that if you want high reliability, you have to have generation on site. The vast majority of outages in the US are caused by disturbances in the distribution system or transmission system. And in the rest of the world, it's insufficient generation. But either way, if you want reliability at your site, you have to have generation at your site. And if the grid's up, great, you don't have to use it. But the concern is when the grid is down, the only solution to that is on-site generation. So, and we're big fans of hybrid systems because a diesel by itself is not a hybrid system, but it's not really sustainable. And as I said, it's noisy, and the fuel costs and emissions, et cetera, are a real problem. But solar and wind don't really stand on their own. They need to be part of a system that includes either storage or a backup generator or both. The world is moving towards renewable systems, and they're going to be hybrids. Even solar plus storage, for example, is a hybrid. These can be very cost effective. There's actually, I wish I just found this report this morning that we're getting new information all the time about just how fast solar and storage costs are declining. In many parts of the world, they are now the least cost source of electricity, even including the storage costs. So it's very cost effective, but there's a lot of degrees of freedom in the design. There's a lot of design variables and decisions that need to be made. It's not as simple as just buying a diesel generator. So it has to be designed right. That's why we created the software. And so I hope this was helpful, that understanding that there's 3 fundamentally different reliability problems, and there's different solutions for each of those problems. And now I'm going to pass it back to Tricia and to Walker and take your questions.
Thank you. Thank you so much, Peter. Hopefully you are seeing my screen now.
Yes.
And thank you both, Katherine and Peter, for really excellent, informative presentations. Before we go to questions, I do want to address one question that often comes up, which is, how do I get started? With HOMER, there are several ways you can utilize UL's expertise. You can use HOMER software to model your microgrid and find the least cost solution, and you can download HOMER Pro or HOMER Grid software for a free trial at homerenergy.com. And to help you dive deeper into the program, we do offer online training, or we have engineering hours where you can bring one of our engineers into your project to help you do the modeling, or we can do the modeling for you. And you can contact support at homerenergy.com to find out more about that. Or if you would like help with the full scope of your project or want to know more about our utility scale front of the meter advisory service, HOMER Front plus UL analysis, you can contact Renewable Energy Services at ul.com to learn more. And if you are interested in learning more about peer, as Katherine mentioned, there are a lot of resources available. You can learn more about peer through the online courses. Upon completion of at least 5 courses and passing the accompanying quizzes, you receive a Peer Pro badge, and the Peer Pro badge offers professional recognition for those who have demonstrated an understanding of the importance of resilience and reliability in power grids and how it can be used to support better buildings and places for people and the environment. And to help you dive deeper into the program, Peer offers many case histories, articles, and technical reports at peer.gbci.org. Or if you're ready to begin the certification of your project and want to understand the process, you can contact peer@gbci.org to connect directly with technical services. So now we'll prepare to go ahead and go to questions. And I'd like to ask Peter and Katherine to share their webcams for the Q&A. And Diwakar Rajaskaran, one of our HOMER software engineers, has been collecting questions during the presentation, and he will be moderating questions for us. Diwakar, what do you have?
Thank you, Tricia. We have a good number of questions here. The first question is, in your experience, how much are users prioritizing resilience over energy savings, renewable targets, or other priorities?
Well, I'll start here, Peter, if you don't mind. I think resilience is something that is being prioritized now more than ever. When you see the impacts of storms and power disruptions, the impacts that they have on businesses, on residents, on operations, I think it is changing the norm from expecting the power to always be there to talking about the challenges in staying up and operational. So resilience is becoming a higher priority.
We're absolutely seeing that as well. People are talking about resilience more than ever, and for good reason. I mean, between the California wildfires, actually the Australian wildfires too, and the floods, like Pakistan had this incredible flooding event that didn't get a lot of press in the U.S. And this ice storm in Texas, we're seeing a lot more interest in it. It's in some ways it is more challenging because it's a little harder to quantify. So the sharpened pencil types are focused more on the energy savings, and sometimes that's easier to talk about. And the value of resilience really varies from place to place in terms of whether it's lost production at a manufacturing facility, but for your emergency services and critical infrastructure, the world has really changed in its attitude about what counts as critical infrastructure. During an extended outage, the grocery store and gas station and pharmacy, et cetera, become critical infrastructure, and not just the hospital and police station. So the world is moving towards a much greater appreciation of resilience. Absolutely.
Thank you, Katherine and Peter. This next question might be for you, Katherine. Is the peer program a tool for designers of microgrids or a tool for operators of microgrids?
It's actually a tool for both. It's a tool that, and we have two parts to the program. You can get a peer pre-certification, which certifies how the project is designed to operate and your forecast of what kind of reliability it's going to deliver. And then after a year of operation, you do a certification of the rest of the credits on how it is operating, how it is performing, and results-based. And that is a full certification in two parts. And then you come back 3 years later and recertify with the hope that you have used the information generated by your program and your tracking and monitoring to identify areas that you could improve.
Thank you, Katherine. This next question is also about the peer certification. Might be a redundant one, maybe you just answered the previous question. But when in the lifetime of the microgrid project do you apply for a peer certification?
Almost any time. We have seen some transit systems. For an instance, we're working in India, and the Delhi Metro is certifying their lines one at a time, certifying the resilience of the power providing that transit system. We have University of Texas Austin, which I talked about earlier, certified their project. They had recently made some upgrades, and so they certified that, but it identified areas where they could make more improvement. And so they made some more improvement and then recertify. So it can happen new construction, it can happen as you're evaluating where you are today, and then you make improvements and you evaluate it later.
Thank you, Katherine. What do you think about using hydrogen as a backup for resiliency or reliability?
Well, that's our whole goal. That's absolutely the right way to improve your reliability and resiliency. That was my main point, I think.
I think hydrogen's a storage mechanism.
Oh, I'm sorry. Did you say hydrogen?
It's a way of storing energy.
I'm sorry. I thought you said hybrid systems. You said hydrogen? Is that the question?
It was hydrogen, yeah.
Oh, I'm sorry. That's a lot of interest in hydrogen. Sorry, Katherine, I kind of interrupted you, but I realized I needed to correct myself. Lots of increasing interest in hydrogen. It's still very expensive, but it's often considered the future.
Especially when it's made with renewable energy.
Well, yes.
So I think they're getting these concepts much better packaged, and so it's a way of storing renewable energy that is produced during the day, and then the hydrogen is something that you can use when the sun doesn't shine or at night.
Thank you. This next one might be an interesting one. So with every utility or region being unique, is the benchmarking of reliability between utilities really a valid exercise, especially with more and more distributed resources? Wouldn't self-benchmarking with goals and progress towards them be more quantitative?
You benchmark to yourself, but I think you also benchmark to nearby systems or adjoining systems. So quite often there is a state average, and so you benchmark to that state average or that regional average as to what is going on, especially when you look at some of your environmental factors and your emissions. So you benchmark to other systems, you can benchmark to other campuses, you can benchmark to other transit systems. Your benchmarking is to some identified averages and within your region.
Thank you, Catherine. This next question might be for you as well. Does the PEER program have earthquake protection recommendations for underground power distribution systems?
It recommends that you consult and advise, and that's one great thing about the program. It does refer you to other data sources to use that information that's available. It does not specifically include earthquake protection guidelines in it, but it refers you to sources and you can get credit or points for addressing that.
Hey, Dwalker, I'm just skimming over the questions, and I see there's a lot of questions that dance around the question of input requirements, and so we're not going to have time to answer all the questions. So I thought I'd have a general answer for these, which is about data requirements for HOMER, and we have databases for much of the inputs, but on almost every parameter, you can put it in, you can override that, or you can put in your own load profiles. You can put in your own. Let me see what some of these questions were about resource data, about temperature. You can either do that manually. We don't hardwire these things, or you can use our databases, or you can put your own data in at various levels of detail. It's more than I can go into here. We have free demos and a free 21-day trial, so you can look at this for yourself. But there's no one way to get the data in, depending on what kind of data you already have. The more data you have, the better.
I just wanted to jump in and let you know we have time for one more question.
Go ahead, Dwalker.
Thank you, Tricia, and thank you, Peter. So we have a question about HOMER here. Do we have any plans of adding any forecasting tools to HOMER?
Well, UL has a forecasting group, and they provide forecasting services, sort of real time for operators of wind farms and solar parks for, I think, over half of all the wind farms in the U.S. So that UL has that capability, and it's our newest version that's designed for HOMER front. It's called HOMER front. It's designed for front of the meter projects. Has a look ahead feature, and which is kind of important for dispatching batteries, and it's very important for minimizing demand charges. So HOMER Grid does it to some extent, and HOMER Pros and HOMER Front is going to, which is in like beta testing right now, is will do more of it. There's two different forecasting issues. One of them is it's multiple forecasting issues. Whether you're talking about the design stage, at the operational stage, it becomes critically important. It's not actually a HOMER issue, but UL's has that capability. It's one of the core capabilities that UL offers to the renewable energy world is, day ahead forecasting. I'm only tangentially involved with that group, but I'd be happy to connect you with them.
Thank you, Peter. Over to you, Tricia.
Thank you so much. Thank you, Diwakar. Thank you, Katherine and Peter, and thank you, audience, for your wonderful questions. Katherine and Peter, you can stop sharing your webcam now as we prepare to close out. But before we go, I wanted to let you know that we are excited to announce the 9th annual HOMER conference, which will be virtual October 12th through 14th. And the conference has a new name this year, HOMER Microgrid and Hybrid Power International. The new name reflects the ever-expanding role of hybrid power as the world moves rapidly along this path to decarbonization and the transition to clean energy. This year's theme is Powering the New Energy World. The call for speakers is now open, so if you would like to submit an abstract, we would love to hear from you. Or if you just want to stay up to date on when registration opens and as we develop the agenda, you can visit microgridconference.com and learn more about the speaking submission or to sign up to stay in touch and learn more about sponsorship opportunities as well. Thank you again for attending today's webinar. If you did not get your question answered, please send it in to our support desk and we will respond to you. And you can watch for an email in a few days with the recording of this webinar. And we hope to see you at our next event.